and you are asked to find out I1 and I2, right? When there is a short like this, why the current need to split and go through this and this? No current flows through a resistor. You have a 14,000 ohm resistance in parallel with a wire. Which will you choose, right? 14,000 ohm resistance with a parallel wire, and the current enters here like I, something like this. Now whether I will choose this 14,000 ohm or this wire, it will choose wire, short wire, because if you have a good bypass road on the city and the city is a worst road with full of vehicles, which will you choose? All people will choose the bypass. In the same way, here no current flows through this 14,000 ohm and all the current flows through this wire here, because that is the easiest path. Hope you have followed, right? I will explain again. Forward bias diode, that you have followed, I think. Both are forward biased. Positive, negative. Positive, negative. It is P side is to the positive, N side is to the negative. Okay, so diode is forward biased. Now next step. If your diode is forward biased, short. Okay, that means this resistor is shorted. 12,000 parallel 0 by 12,000 plus 0. R1 R2 by R1 plus R2. Total is 0. So replace it. This resistor and wire here, this is a short, I2 is current passing through this is a short here. What about this one? This resistor is live. But when current enters through this, current need not pass through 14,000 ohm. All the current flows through this, because this is the easiest path, short wire. So whenever you have a short wire and a resistor, current selects the short wire. Maximum current passes through this, no current passes through this. So I1 is 0. One conclusion. What is the current through this wire? That is the current in the circuit, right? Now the whole circuit will be like this, 10 volt, okay, and a resistor here, that is 2000 ohm, 2 kilo ohm, and whole short, and like this. This is I1. What the current flows to this shorted wire like this. Okay, so what is I1? I1 is equal to V by R. V is 2000 by R is V is 10 volt by 2000. 10 volt by 2000. 1 0 cancels. 1 by 200. 1 by 2 is 0.5. 1 by 20 is 0.05. 1 by 200 is 0.005. So 0 and 5 milliampere. Is it milli? Yeah, 5 milliampere, right? 1 by 200 is 0.0, 1 by 2 is 0.5, 0.05, 0.05, yes, 5 milliampere. 0 and 5 milliampere, option D. Yes, you have to realize it, that's all. 34, we'll finish it. What is the Boolean expression for the gate shown here? Okay. Right. What is the Boolean expression for the gate circuit shown below? This one, yes. An AND gate, and with a NOT gate, I will directly connect it like this. A, only is the input. A. Here A comes, and this is A bar. Y is equal to AND gate. A dot A bar. Where is A dot A bar? Oh, here should be one A bar, I think. Bar is not seen anywhere. A dot A bar it should be. Something like that. A dot A bar. And this is always equal to 0, because you give 1 or 0 to A. If A equal to 1, what will be the answer? Y is equal to 1 dot 1 bar. 1 dot 1 bar is 1 dot 0. 0. Remember AND gate. When one of the input is 0, output is 0. Then if A is equal to 0, what is A? Y is equal to 0 dot 0 bar. 0 dot 1, that is also 0. So this should correct this answer. A dot A bar is equal to 0. Option 2. And it is correct in the question paper. Okay. 35. In the circuit shown, the current I is, here is a diode, not symmetrical, yes, diode and a resistor. 100 ohm plus 3 volt and plus 2 volt. P side, N side. P side is at lower potential, N side is at higher potential. Plus 3 is greater than plus 2. Reverse bias diode, no doubt, 0. Suppose it was ulta, 3 volt and 2 volt, then what would have been the current? Current is equal to 3 minus 2, of course, V by R, 3 minus 2 by R 100. 1 by 100, 0.01, 10 milliamperes, that's all. Okay. Right. Now it is 0. 36. A full wave rectifier is being used to rectify an alternating voltage of frequency 50 Hz. Full wave. The number of pulses of the rectified current obtained in 1 second is per second. Number of pulses means frequency. Number of pulses per second. It should be 100, right? For full wave rectifier, it should be double. Input is 50. Output is full wave 50 only, right? No, 100. Full wave 100. Half wave it is 50. Yes. 37. The average value of output current for a full wave rectifier. Average value is 2 by pi times I naught current. Whereas for half wave it is only I naught by pi. 1 times I naught by pi. For full wave it is 2 times I naught by pi. And similarly average is I naught by root 2. Full wave. Half wave I naught by 2 only. Okay. It's a direct question. Second option. 38. The output current versus time curve of a rectifier is shown in the figure. The frequency output shown is 200 Hz. What is this output curve? Full wave, right? Output frequency is 200. What should be the input frequency? 100. It should be half. Output is 200. Input should be 100. If input is 100, output is 200. Full wave rectifier. For one cycle of input, like this, it shows the same type of variations twice. So it is 2f. 2f is 200, f is 100. Yes. So here is the 39th question, right? A and B are inputs and X is the output. Following timing diagram represents dash logic gate. So in these types of problems, it looks very horrible, but it is a very, very easy problem. Very easy problem. What you have to do is, between these two time intervals, what happens, you should go on checking. First you write the truth table, A, B and X. You be ready with the truth table first. Now, you write all the possible combinations, 0, 1, 0, 1, 0, 0, 1, 1, like this. Now you check this here, between these two time intervals, this one. What is the case? 1, 0, 1, 1, 0, 1. Yes. What about the interval, this one, between these two intervals? 1, 1, 1, right? Here is 1, here is 1, here is 1. Because this is 0 and this is 1. This is 0 and this is 1. Lower value is 0, higher value is 1. So what do you get in this time interval? 1, 1 and this is 1, right? We have, yes, 1, 1 and 1. 1, 1, 1, yes. What about the third one? This interval, 0, 1, 1, 0, 1, 1, 0, 1, 1. You have to go in the order A, B, X. 0, 1, 1. Last time interval here. 0, 0, 0. 0, 0, 0. You see, only when both the inputs are zeros, output is 1. Any one of the input is 1, output is 1. So option is OR gate. First option, correct? So that is the answer. So very easy problem. We will have two more questions here in the same time. Okay. Then 40th one. See the output timing diagram. We call it as timing diagram because at the same time what happens to the input and output, that's what we have to discuss. A, B, X again, and we'll write all the possibilities 0, 0, 1, 1. Okay, we will go to this gap, time interval. This interval gives 1, 0, 0, 1, 0, 0, 1, 0, 0. Okay. 1, 0, 0. Here 1, 1, 1. 1, 1, 1. Yes. This is over. This one. 0, 1, 0. Right? 0, 1, 0. Yes. 0, 1, 0. Okay, 0, 1, 0. What about this one? 0, 0, 0. Last one, correct? All are zeros. 0, 0, 0, 0, 0, 0. So higher level you take it as 1, 5 volt, 0 volt, 5 volt, 0 volt, like this. So this is 0, this is 0, this is 0, this is 1, 1, 1, 0, 1, 0. Okay, all are over. Which gate is this one? When one of the input is 0, output is 0, and this is AND gate, right? This is the option, and that is the correct one. Second one, correct? Okay. 40th over. 41st. Similar type of question. Okay. A, B, and what is the output here? F. 0, 0, 0, 1, 1, 0, 1, 1. Yeah, we will write, start from here. This is 0, 0, 0. First one, up to here. 0, 0, 0. Okay. And this is 1, 0, 0. 1, 0, 0. Okay. Then this is 0, 1. I will write it here. 1, 0, 1, 0. 0, 1, 0. Now you have to search both 1. Anywhere with both 1. 1, yeah, 1, 1, 1. See this here. 1, 1, 1. Again AND gate, right? That is the correct answer, right? Option 2 again. Very simple, right? We will go to 42. Yes. Universal logic gate among the following is NAND gate. There is no NOR, right? Option 4. Need not discuss. Option 4 is the universal logic gate. 43. Yes. Very simple output. What is the output of the circuit? Very simple. You can do it here only. OR gate, right? It is OR. It is not AND. It is curved like this, little bit. It is very confusing one, like this. But this is curved. This is curved. So OR gate. A plus B here. I'll write it here only. A plus B. And that is added to C. A plus B plus C here. And it is added to D. A plus B plus C plus D. That's all. Option 4. Right? OR gates one by one, take the outputs and take the another fresh input, keep on OR, and that is A plus B plus C plus D. For the following logic gate, y is equal to 1. Which one of the following options are correct? You have to check it one by one. We'll check it. First we'll write the circuit. NOT gate to an OR gate. Is it OR or AND? It's OR, because this is bent like this. So it is OR, and then and here is an OR like this, and here is one input, that is B, and this is taken here. It is given to another NAND gate, and from here it is complemented, and this is given to this one. Is it okay? Okay. We will check one by one. A0, B1. Circuit is okay. A is here. 0, B, and output Y here. They want output Y equal to 1. 0, 1. 0, 1. Not 1. 1. Same input. 1, 1 or 1. 1. 1 not 0. A 0, 0. When the input of 0 is 0, 0 is given to AND gate, output is 0. NAND gate 1. So this is 1. This is NOR, not OR. 1, 1 input means OR gate output is 1, NOR 0. So not possible. We have to rub this. Second one. We will check the second one. Yes. And there is no other shortcut, isn't it? Yes. Is there any shortcut? B1, B1, B2? Yeah, maybe. Because directly that is not fed to the last one. So you have to check it. Yeah, next possibility. 1, 1. 1 and 1. 0, 0. And this 1 comes here. When input to the OR gate is one of them is 1, 1, 1. Okay, then here 1 becomes 0 and this one will be here. And AND gate gives output 0, 1, 0. One of the input is 0, AND gate output is 0. NAND is 1, 1. For NOR gate, 1, 1 if it is the input, OR is 1, output is 0. No use. Third one, A1, B0. Let us pray God that the third option is the correct one. Or shall we come from the fourth one? If it is right, then we will get the answer quickly. Let us start from the third one. A1, B0. A1, B0. Okay, 0, because not. 1 comes here, 0 comes here. When OR gate input is 0, 0, output is 0, 0, 0. What about this one? 1 and this is 1, 1, yes. 0, not 1. This one is here. When 1, 1 is the input to AND gate, output is 1. But NAND, 0, 0. Got it. OR gate output is 0, NOR is 1, J. Third one is the correct answer. Last one, we check it yourself, right? I don't do that. Okay, shall we move on? The last question. 45th one. The energy level formed due to impurity atoms. Yes. In the forbidden energy gap. Very close to the valence band in a p-type semiconductor. Yes. Suppose you take an intrinsic semiconductor, say silicon. Its energy level diagram is like this. This is conduction band and this is valence band, and this energy gap is very less than 3 electron volt. Silicon 1.1 electron volt or 0.7 electron volt. Energy gap is very less. Now, once you dope it with the, so at 0 Kelvin, all the electrons will be in the valence band. No electrons are in the conduction band. But as the temperature increases, if you bring this to the ordinary room temperature, using the heat energy, the electrons will go to the conduction band. It becomes a partial conductor. That's why we call it as semiconductor. Now, that produces equal number of electrons here and holes here. Holes are found in the valence band, and electrons, free electrons I am talking about, are found in the conduction band. Okay, now it is a partial conductor. Now if you dope it with the what impurity? P-type semiconductor. That is trivalent impurity. What happens? Some more holes will come into the picture, and these holes are the holes created, that is vacancy of bonding electrons because of the deficiency of one electron in the boron atom or any trivalent atom. Now where do these electrons lie? Where do these holes lie? Not electrons. So when you add trivalent impurity, holes are created. Where do they go? Do they go to valence band? Do they go to conduction band? They are the holes of dopant atom for an impurity, and they don't join with these valence band holes of silicon. What do? They form their own colony. Very close to the valence band there is a energy level, that is called donor level. So donor level is the energy level of those holes which are from the doped atoms, and they are very close, just above the valence band, and that is called donor level. Similarly, if you dope a silicon with the pentavalent impurity, then electrons, free electrons will be extra will be found, because that doped impurity will have more valence electrons. So many valent electrons are not needed for silicon. So those extra valence electrons, they will form the free electrons, and they will form their own energy level. That energy level will be just below the conduction band, and that is called this is acceptor level. This is acceptor level, and this is donor level. Because pentavalent impurity donates one free electron. Trivalent impurity creates a shortage. It is ready to accept. So the energy level of the trivalent holes, which are just above the valence band, is called acceptor level, and the energy level of pentavalent electrons, dopant electrons, just below the conduction band, this is called donor level, this is called acceptor level. So what is the question now? Acceptor level? No acceptor level. The energy level formed by the impurity atoms of the forbidden energy gap, very close to the valence band in a p-type semiconductor, is acceptor level. You have to change this. Acceptor level, not donor level. Donor level is here. It donates one free electron. This is acceptor level. So acceptor level is because of holes. They are very close to the valence band, just above the valence band. Donor level is because of doped electrons. They are just below the conduction band. Okay. So with this we'll complete semiconductors. If time permits, we will have more questions in the coming days, right? If exam is postponed by chance at the last moment. Okay, thanks for watching the video, and if at all you have doubts, you please ask me through text or voice or written form in the WhatsApp. Keep working, don't waste time. Take care of your health. Thanks for watching the video. Thank you.